Good evening, everybody. This is the second last class of Anova. So, today I am going to discuss application of the relation application of the technique of analysis of variance Anova in the study of relationship. First, consider test for the relationship between two variables. Suppose x have p levels, where x correspond to independent variable and has p levels, and level of these levels are denoted by x1, x2, xp. And assume these are, or the variable x is non-stochastic. Y is a dependent variable and we arrange the observation as follows. That is, we have some observations on the dependent variable y as follows. Corresponding label x1, we have n1 observation, and I denote this observation by y11, y12, yn1. Corresponding label x2, we have n2 observation, and we denote this observation as follows. And lastly, for kth level, we have NP observation. The first question, do the variable, do the do the available observations provide any evidence that two variables x and y are related in their movement. So, answering this question, we assume that Yij, the jth observation corresponding ith level of x, is equal to mu y plus ei, where mu y is a column effect and Eij independently identically normal 0 sigma square. So, where sigma square is 1. If the values of y do not depend on the values of x, then we expect mu1 equal to mu2 equal to mu. Hence, null hypothesis h naught is equal to mu1 equal to mu2 equal to mu p, that is absence of relationship. versus alternative hypothesis. H1, that is H0 is not true. That means at least one mu I is different from others, which means presence of relationship. So for testing this, we use one-way Anova. So this is the case of one-way classification of data. And the Anova table as follows. First column is source of variation, source of variation. Second column is degrees of freedom. Third column is sum of squares, MS. Units. And last column is F ratio. So between arrays, degrees of freedom P minus 1 is form good evening. Between arrays P minus 1, between arrays, you knew all these things. This is the, I think this is the day 1 or day 2 class. This is just one way Anova. Within array, it is n minus p I from 1 to p a9 yi not bar. You know all these notation, so that's why do not define this again. Those who do not understand this notation, please go through our previous class of Anova. All the videos you can find videos in our channel. So please check. I from 1 to p, j from 1 to ni, yij minus yi not bar full square. And this is the total n minus 1 sum over I from 1 to p, j from 1 to ni, yij, y not bar full square. So Image B, in this image B is nothing but a self-pick by corresponding degrees of freedom, that is P minus 1. Image E or image W, mean square within array. Mean square within array is nothing but SSW, sum of square within array by N minus P. You can also, it's that same thing, SSW is nothing but SSE. So MSW also same as a MSC, mean square due to error. Mean square due to error same as mean square within array. And if ratio, this is equal to MSB by MSW. We reject H naught at level alpha if F ratio calculated value of A is greater than F alpha P minus 1 A minus P, where F alpha P minus 1 A minus P is a upper percentile point of A distribution, upper alpha percentile points of A distribution with P minus 1 A minus P degrees of freedom. Now, the null hypothesis of absence of any relationship between X and Y will be rejected at the level alpha if the value of A obtained in the above table exceeds F alpha P minus 1 A minus. So this means these are the same thing. In the above test, we have made no assumptions about the form of relationship whether linear or non-linear, because from this test we can only say whether these two variables are linearly related, whether these two variables are related or not. But we cannot say if H naught is rejected, we cannot say whether this relationship is linear or non-linear. So So this means so we have tested for the presence of any relationship and the rejection of the null hypothesis it suggests that there is some relationship. So the next step is to test for the linearity of equation. So if H naught is rejected, that means after the relationship is established, the next step will be to find the appropriate regression function so first we try to find out the simplest function that is linear regression. Which fits the observed data. So the null hypothesis is mu I is equal to alpha plus beta xi with some with the same observational equation as in case 1. That means which I just discussed. So the model is Yij, which is equal to mu I plus Eij. Now, first we minimize, I define S1 square, which is minimum with respect to mu I, sum over I, j, I from 1 to p, j from 1 to ni, Yij minus mu I whole square. And we know this is nothing but a sum over I from 1 to p, j from 1 to ni, Yij minus Yi naught bar whole square. Know this with degrees of freedom n minus. Now S2 square, which is again minimizations of this sum of square, Yij mu I. This minimization not only based on mu I, also H naught, that is mu I equal to another constant mu I equal to alpha plus beta xi. So therefore now the parameters is unknown parameters is 2, that is alpha and beta. So and you get same process, you already knew all these things. This is the fundamental theorem of linear hypothesis. Just I apply this, and you know how to minimize this, just taking the partial derivative with respect to alpha beta, and then you get this sum over I from 1 to p, j from 1 to ni, Yij minus Y naught naught bar minus b xi minus x bar whole square, where b equal to estimate of least square estimate of beta hat, which is sum over xi minus x bar yi not bar minus y not bar. So sum over I from 1 to p, ni into xi minus x bar into yi not bar minus y not bar divided by I from 1 to p ni xi minus x bar whole square, where x bar is sample mean of x. So this is equal to sum over one by n sum over I from 1 to p ni xi. So please check if you minimize this, then you get this thing. This is your homework. Please check this. Now, this H2 square can be written as I from 1 to p sum over j from 1 to ni yij minus y naught naught bar whole square minus b square sum over I ni xi minus x bar whole square. So please check this thing, you can get from this to this. This is another homework. And this follows chi square with p minus, no, actually I want to say firstly like this. This is with degree of freedom n minus 2 and so under H naught this S2 square follows sigma square into chi square with n minus 2 degrees of freedom. Similarly, this S1 square follows sigma square chi square with n minus p degrees of freedom. And again, S2 square minus S1 square, this gives sum over I from 1 to p ni yi naught bar minus y naught naught bar whole square minus b square sum over xi minus x bar whole square. Sorry, please add this term ni into xi minus x bar whole square. And this is follows under H naught chi square with p minus 2 degrees of freedom into sigma square under H. And these are independent, S2 square, S1 square, and S1 square is independent or independent. Just use the Occam's theorem. Then under H naught, the F, which is equal to S2 square minus S1 square by P minus 2 whole divided by S1 square minus n minus p follow F distribution with p minus 2 n minus p degrees of freedom. The hypothesis of linearity of regression is rejected, at the level alpha, if this f is greater than f alpha p minus 2 n minus p degrees of freedom. This is the upper alpha percentile of a distribution with p minus 2 n minus p degrees of freedom. Now, we can write sum over ij, I from 1 to p, j from 1 to ni, yij minus y naught bar, which is a total sum of square. This can be written as SSW within sum of square, SS DLR, departure from linearity, SSLR, sum of square due to linear regression. Okay, so where SSW sum of within sum of square or sum of square due to within variation. So this is equal to sum over I from 1 to p, j from 1 to ni, yij minus yi naught bar whole square. SS DLR, this is SS due to deviation from linearity, or it is better to say linear regression, which is equal to this S2 square minus S1 square. Please write this expression here, that is sum over I from 1 to p ni yi naught bar minus y naught bar whole square minus b square summation I from 1 to p ni xi minus x bar whole square. So please write this here. SSLR, which is SS due to linear regression, so this is equal to b square sum over I from 1 to p ni xi minus x bar whole square. So then, if you look at this F ratio, that is F, which is equal to S2 square minus S1 square by P minus 2 by S1 square L minus P. So this is nothing but a SS DLR sum of square due to departure from linearity by SSW sum of square due to within variation into n minus p, p minus 2. So these two are same thing. These two are same. And this is again we write ms dlr by ms w. So this is the statistics used to test for linearity of regression. If the ms due to deviation from linear regression is significantly different from that is greater than the ms due to error, then we have reason to doubt the linearity of regression. If we denote alpha hat plus beta hat xi by capital Yi, where this is the predicted value of ith observation, where alpha hat and beta hat are the least square estimate estimator of alpha and beta, then you see that SS LR sum of square due to linear regression, which is written as sum b square equal to sum over I from 1 to p ni xi bar minus xi minus x bar whole square xi minus x bar whole square. So this is nothing but a I from 1 to p ni capital Y yi minus y naught naught bar whole square. So please check, this is your another homework. And SSDLR, which is equal to sum over I from 1 to p ni yi naught bar minus y naught naught bar whole square minus b square sum over I ni xi minus x bar whole square. This is equal to sum over I from ni yi naught minus yi naught bar minus yi bar yi capital yi whole square. So here we know this is another homework. So we know alpha hat, which is nothing but a yi naught bar. Just check this thing. Beta hat x bar. Actually, this is not yi, this is y not bar. Please check this thing. When as beta hat x bar and beta hat, you can use, this is the yij. Just use the least-square estimator, okay? Just use least-square estimator of just, I think, define this term. Okay, this is simply b. So this is equal to sum over ni yi not bar minus y not bar xi minus x bar by summation ni xi minus x bar whole square. Okay, so first you derive this part and use this thing here and here, you can get the result. Okay, so now the Anova table, for linearity of regression. So first column is source of variation, source of variation due to linear regression due to deviation from linear regression between arrays within arrays total degrees of freedom. So due to linearity, this degree of freedom is 1. Due to deviation from linearity, this is p minus 2. This is n minus p. So between array, this should be p minus 2 plus 1, that is p minus 1, adding these 2. So it is better to divide this portion. Now within array, this is n minus p. So if you add all this p minus 1, n minus p, this gives n minus 1, total degree of freedom. So SS, to write it, the expression of SSLR here, SSLR equal to, is write the expression of SSLR. SS DLR, that means deviation from linearity, is write the expression. SS D sum of square between arrays, we write the expression SSW, sum of square within variation, we write the expression SST. MS, which is MSLR, this is nothing but a SSLR divided by corresponding degrees of freedom, that is 1. So MS here MSLR and SSLR are same. MSDLR. So this is equal to SSDLR divided by corresponding degrees of freedom T minus 2, and MSB, MSW, and F, since here we interested in linearity of regression, so F equal to MS DLR MS DLR divided by MS W. So find this F ratio and check whether is the critical value, whether this N exceeds this critical value. So if 8 is rejected, if a H0 is rejected, that means Y is not linearly related. So we go to the next step. So that is, if the F at the previous stage is significant, then the hypothesis H0 mu y equal to alpha plus beta xi fails to account for the relationship between x and y so we may try various hypotheses regarding the form of the relationship between x and y. In this way, we may examine successively whether a polynomial in X of degree K, we denote this by capital P within bracket X, will be able to explain the relationship for K equal to 2, 3, but K should be less than. So that means if linearity fails, then you go quadratic, cubic, fourth degree polynomial, and so on. This is the process. So first linearity fails, then you try quadratic, second degree polynomial. If this is failed, then you try third degree polynomial. If this thing is failed, then you try fourth degree polynomial, and so on. This is the process. Okay, so I discuss here the generally, but for particular case, that is when the data is given, you follow these steps. So where P is a number of Y arrays. Here the null hypothesis mu equal to alpha plus beta 1 xi beta 2 xi square beta k xi k, that is the relationship between x and y can be explained by a polynomial of degree A. Let alpha hat, beta I hat are the least square estimators of alpha and betas, and let P hat k xi, the estimate of pk xi is equal to alpha hat beta 1 hat xi beta 2 hat xi square beta k hat xi k. Then same way, using the same procedure, the total SS can be partitioned as summation I from 1 to t, j from 1 to ni, yij minus y naught naught bar whole square, which is equal to SSW plus SS drk, departure from k degree polynomial regression, SSRK, this is sum of square due to k degree regression, say, where this SSRK is due to polynomial regression of degree k, which is equal to, same way you can write this, sum over I from 1 to t ni pk hat xi minus y naught naught bar whole square. This is dk, departure from k degree polynomial regression, that is, this is due to deviation from this regression. So this is equal to sum over I from 1 to t ni yi naught bar minus pk hat xi whole square. So the Anova table, we can construct Anova table for this hypothesis as this is due to regression, that means pkx, and the degrees of freedom should be, instead of k, this should be, instead of 1, this should be k, because we consider k degree polynomial. Due to deviation from regression, this should be p minus k minus 1 instead of p minus 2, because the first case I consider the linear, that's why this is p minus 2. So generally it is p minus k minus 1. So these are the same thing, and this should be, S is due to not LR, this is RK, this should be not DLR, this should be DRK, and here change this thing, image RK, which is this is into RK divided by corresponding degrees of freedom K. It's an image DRK, which is equal to SS DRK divided by corresponding degrees of freedom, that is P minus K minus 1, and the F ratio is MS DRK divided by MSW. This is the F ratio. So similarly, we reject H naught if so we reject H naught, that is k degree polynomial at level alpha if a greater than f alpha with degree of freedom p minus k minus 1 comma n minus, otherwise accept. Okay. At level up. So, but this is a huge computation involved this thing. So you can use, instead of this polynomial, you can use orthogonal polynomial to reduce this labor. So the computational labor in this case can be reduced by picking orthogonal polynomials. Okay. So please tell me, can I wrap this question? If you finish this thing, please tell me, can I wrap this question? Only are you hearing me? If you finish this, please tell me. I'm waiting. So for the definition of orthogonal polynomial, you can see any book, statistical book, or you can from internet you can also find this definition. So if you have a problem with a orthogonal polynomial, so please tell me before the last class that will be held on Monday, coming Monday. I will definitely discuss orthogonal polynomial. So, can I? Oh, okay. Thank you, Pauline. So next part is test for the homogeneity of a group of regression coefficient. So suppose we have P groups of observations on x comma y. The observations in the I group may be labeled xij, yij for j from 1 to n, I from 1 to p. We can then have P regression equation corresponding the regression of y on x as follows. That is, model is expectation yj alpha I plus beta j xi j minus xi alpha. Then, under the assumptions that yij are independently normal with variance yij equal to sigma square for all group, and obviously expectation of yij equal to alpha plus beta j, sorry, beta I and beta j. This is beta I xij minus xi naught bar, alpha I plus beta I xij minus xi naught bar for all, and variance of yij is constant, that variance of yij is equal to sigma square for all groups. So this is for the assumptions of homosphericity. We may be interested in the null hypothesis H naught, all beta I are equal, or in other words, the hypothesis that the P regression lines are parallel to one another. So that means, since slopes are same, that means this thing is there. all beta i's are same. This means all regression lines are parallel. So the least square estimate estimators of alpha and beta I are alpha I hat is equal to y I naught bar, because if you write this model that way, this means alpha I and beta I are orthogonally estimated. You can take this statement, or you can find the alpha I beta just minimizing the sum of square dk error with respect to alpha I beta I respectively. And beta I hat this is equal to sum over j xij minus xi naught bar yij minus yi naught bar divided by sum over j xij minus xi naught bar whole square. And I denote this by small bi. See. Now, S1 square, which is unrestricted residual SS, and this is equal to sum over I j yij minus yi naught bar after replacing alpha I and beta I hat in beta hat, then you get this. I think it is better to write in that way fast. Yij minus alpha I hat minus beta I hat xij minus xi naught bar whole square equal to sum over I, sum over j, yij. Now replace estimate of alpha I, beta I hat, then you get bi xi naught bar whole square. So this is equal to sum over I j yij minus yi naught bar whole square minus summation I bi summation j xij minus xi naught bar yij minus yi naught bar, and I denote this term by capital Ci, then this is equal to I from Ci, and this term by capital Bi. So this is equal to sum over I Bi capital Bi. So therefore this is equal to sum over I Ci Bi capital Bi, which is nothing but a unrestricted residual SS for ith group. This thing are same. If you look at the expression, so this is the unrestricted residual for ith group. So the degrees of freedom for unrestricted residual for ith group is n minus 2. So the total degrees of freedom for this S1, this is unrestricted residual SS. This is should be sum over I from 1 to P Ni minus 2, and which is equal to n minus 2. So now H2 square, this is minimum value of some double summation ij yij minus alpha I beta I xij minus xi not bar whole square when minimized with respect to alpha I beta, because under H naught all beta is same and I assume this is equal to beta. So instead of beta I write beta, which is beta is a common value of beta is under H naught. Okay, so then it's equal to, if you replace the least square estimate of alpha and beta, then you get yij minus yi naught bar minus b xij minus xi naught bar whole square. And if you simplify this thing, you can get yij minus yi naught bar whole square minus b summation ij xij minus xi naught bar yij minus yi naught bar. And again, same way you can write this as capital Ci square. I already defined Ci, so this is equal to capital Ci, sorry, this is capital Ci minus b into sum over I capital Bi, and this is equal to, I write this sum of Ci by capital C, and this is by capital B, and the degrees of freedom, because now it is ni minus 1, so it should be ni minus 1 minus 1 I from 1 to P, so this should be n minus P minus 1 degrees of freedom, where the least square estimate method under H naught of alpha I and beta are alpha I hat, which is yi naught bar, and beta hat, which is equal to sum over I, sum over j, xij minus x naught naught bar, yij minus y naught naught bar divided by, sorry, this should be, these are the same thing. Please check. Okay, I think this should be xij minus xi naught bar, yij minus yi naught bar by summation ij xij minus x I naught bar whole square. So please check, these are your homework. So thus the test of H naught is obtained by using the test statistics. A, which is equal to S2 square minus S1 square by S1 square into corresponding degrees of freedom, that is n minus 2p by p minus 1, because S2 minus 1 S2 square minus S1 square degrees of freedom is p minus 1, because if you subtract this n minus p minus 1 from n minus 2p, then you get degrees of freedom. Okay. So under H naught, this follows a distribution with p minus 1 n minus 2p degrees of freedom. We reject H naught at level alpha if is f greater than f alpha p minus 1 n minus 2p. So now the Anova table first column is source of variation, second column is degrees of freedom, third is SS, then MS, last is F ratio. So source of variation, first is difference, this is total minus within group, then within group, then total. So this should be S2 square minus S1 square, this is equal to S1 square, and this is S2 square. So degrees of freedom is p minus 1, then n minus 2p, n minus p minus 1. First n is due to difference. So this is equal to s2 square minus s1 square by e minus 1. Then image w, which is equal to s1 square by n minus 2p, and f is the image r by image w, which is f. Okay, so if you finish this, please tell me. Can I wrap this portion? This is the last topic which I want to discuss. This is the last topic for today class. Okay. So please follow me. Tell me, can I wrap this portion? So next topic, that is, okay. Thank you, follow me. Test for equality of regression equation from P groups. If we have P different groups, then having used P different regression equation, we may like to know whether these P equations are identical or equal. If so, then the prediction formula for one group may be used for the other P minus 1 groups also. We assume the model expectation of Yij, which is equal to alpha I, beta I, Xij minus Xi naught r. And Yij follow normal distribution independently with variance of Yij is constant, that is sigma square for all I j, where sigma square is unknown. Again, the same way you can write the unrestricted residual S1 square, which I already defined. Just see the when the test corresponding to the all the slopes are same or parallel. All the slopes are equal. That means the all regression lines are parallel. That is 4. This is 5, just previous one. Okay, this previous one. So this will be capital Ci, Bi cap, small bi, capital Bi. I already defined this term, Ci, capital Bi. And in degrees of freedom, this is equal to sum over I from Ni minus 2, that is n minus 2. Okay. Next is 2 square. This is called unrestricted residual. For unrestricted residual SS, and this is restricted residual SS. And this is again we can write, just see the C minus B naught the same way, where capital C, this is equal to sum over Ij Yij minus Y naught not bar whole square. Capital B, this is equal to double summation Ij Xij minus X naught not bar Yij minus Y naught not bar. With degrees of freedom, this is equal to n minus 2. And the P naught is a least square estimate. Estimator of common regression coefficient. B. Sorry, beta, and this is equal to sum over I, sum over j, xij minus x naught not bar, yij minus y naught not bar, double summation ij, xij minus x naught not bar whole square. And similar way you define the ratio. This is equal to S2 square minus S1 square by S1 square. The degrees of freedom of S2 square minus S1 square is 2 into P minus 1, and this is equal to N minus 2P. Okay, so now the Anova table. Source of variation, due to H naught, residuals, and this is residual under H naught. and degree of freedom is 2 into p minus 1. This is n minus 2p n minus 2. Ss due to h naught, this is s2 square minus s1 square. This is s1 square and this is s2 square. Ms s2 square minus s1 square by 2 into p minus 1. You denote this by ms d2 h naught. So this is equal to ms d2 h naught equal to s2 square minus s1 square by 2 into p minus 1. Ms d2 residual or due to error, this is equal to s1 square by n minus 2p, and F ratio, this is equal to ms h naught by mse. We reject h naught, that is all the regression equation are same at level alpha if the F ratio F is greater than F alpha 2p minus 1 n minus 2p, where this F alpha, this is alpha 2 into p minus 1 n minus 2p, and these are F alpha 2 a p minus 1 n minus 2p, the upper alpha percentile distribution with degrees of freedom 2 into p minus 1 n minus 2. Otherwise we exclude. So this is all about the today class. My last class that will be held on Monday at the same time 6 p.m. So the last topic I will consider, that is the test for multiple regression model, multiple linear regression model. So this is the last topic of my class that will be held. The last class will be held on Monday, Anova. Okay. So have you any queries or questions? Please tell me. If you have no question, then please mention in the comment section. Then I close this video. And have you any question? Then you write this in the comment section. I will address your question. Okay. So please take your time and tell me. Okay, thank you, Polumi. So we'll meet again on Monday, same time 6 p.m. This is our last. This will be the last class of Anova. So till then, please watch please wait and stay with us. Till then, stay with us, and thank you for watching this video. Thank you.